are graphing is they think that the x and the y-axis are out of the picture. They're no longer part of the graph, and that's not true. So when you look at this little bullseye graph that I have drawn up there, this right here, this is still the x-axis. That has not changed at all. And this is still the y-axis. Again, hasn't changed at all. Still the x, still the y. But instead of a grid in which we have all these vertical grid lines and horizontal-ish, I'm doing my best, grid lines. Instead of having all those grid lines on there, we almost think of it as like these concentric circles that express distance from the origin. Does that make sense? So, like, technically the grid lines are still kind of there. And the x and y axis are definitely still there. But we just don't draw the grid lines on there because it's going to turn into this big old mishmash of, like, lines, and it's going to be really confusing as to what is actually what. Does that make sense? So all those things are still in place, but we're going to focus on graphing in a different way. So if you were going to try to graph just a polar coordinate, like in other words, just a point on the graph, instead of getting an x-coordinate and a y-coordinate, you need an r and a theta. Now, what do you think the r stands for? Yeah, it stands for a radius. I think a good way of thinking about this is distance from origin. Probably a better word would be displacement from origin, technically. And, in polar coordinates, we sometimes refer to the origin with a different word. Has anybody ever heard of a different word for the origin? No? Okay, so sometimes we refer to the origin as the pole. You know, like the North Pole, the South Pole, that sort of thing. Okay, so R stands for radius. What would you guys guess theta stands for? An angle. Theta does stand for theta, yes. And we're going to be specific here. Angle from, not from the origin, not from the center. Yeah, the positive x-axis, 0 radians, 0 degrees. Yeah, so angle from 0 radians, and that would be the positive x-axis. So we'll graph that 2 comma 4 pi over 3 here in just a second. But before we do that, if I drew something in here, maybe, I don't know, something like this. So my point is right there at the end of the arrow. So that coordinate could be represented in polar coordinates. And the polar coordinates for that, let's think this through. What do you guys think the radius, what do you think the distance from the origin would be for that particular point? It'd be 2. And what's the radian angle? That's the positive x-axis, so it'd be 0. So what's interesting about that, so 2 comma 0, that's actually, isn't that also the rectangular representation of that point as well? Pretty strange, yeah. So whenever you're on the actual axes, I think you'll find, like the positive x-axis there, I think you'll find that the rectangular coordinates and the polar coordinates should be the same. But anytime you move off the positive x-axis, they will be very different because they stand for different things. And so I thought we could graph this 2 comma 4 pi over 3 over here. So to me, the easiest way to handle this is to graph or think about the angle first. So in which quadrant is 4 pi over 3? Third quadrant. So we're pointing roughly that direction. Is that fair? So we've rotated our direction, and now we're facing into that third quadrant. Do you see it? Facing into the third quadrant. So I suppose if you want a super high-tech demonstration, here I am. I'm facing the positive x-axis. All I've done here is I've rotated, and now I'm facing into the third quadrant. Make sense? So I'm facing the correct direction, and now the 2 is telling me to essentially walk forward 2 units. And so I would, now that I'm facing that direction, I would proceed to move forward, and I would be right there at the end of that arrow. This would be the polar coordinate 2, 4 pi over 3. Make sense? Okay, so I've written this down there at the bottom. You can kind of see it on your paper as well as up there. I put there that polar coordinates do not have unique representations. There's an infinite number of ways for you to arrive at the same place using polar coordinates. Let me give you some examples of that. I could get to that purple point in a number of ways. The way that I just did it is I turned positive 4 pi over 3 and walked straight ahead 2. Couldn't I have also rotated a negative angle? Let's see here. That would be pi over 2 plus a pi over 6, right? So it'd be 2 pi over 3. So I could have rotated negative 2 pi over 3 and been facing the correct direction and walked forward 2. So there's 2 ways I could have got to that point using polar coordinates. But there are other ways. Can you think of another way, another totally distinct way for me to get to that same spot, but not following the purple or the blue path? What do you think, Johnny? Go all the way around? So in other words, like, go that? Yeah. I can't do that very many times without getting dizzy. That was almost my limit. Sure. So why couldn't we do what Johnny suggested and go around a whole circle and then around again and get to be facing that same direction and then walk forward 2? So spin around multiple times. And of course you can start to see how we could build off that, couldn't we? Emma could be like, no, spin 2 whole times. And then go a little bit further, right? Josiah's like, no, go 5 times around. And we could one-up each other forever and ever. And you start to see the infinite pattern, right? Okay? But there is another totally distinct, different strategy you could take. Beyond the, hey, just spin 1 more time. What do you think, Colin? So let me hear what you said again. You said negative 2 comma something? Pi over 3. Okay, so let's think about how this would work. So I'll graph this in a lovely orange color. So now he's telling me just only turn to pi over 3. So turning to pi over 3 would be, I don't know, something like this. Can you see that orange in there okay? So now I am facing this direction. And can you see how that direction is exactly the wrong way? It's exactly the wrong direction. 180 degrees or pi radians away from where I need to be facing. But then he fixes it by saying, don't walk forward, walk backwards. So at this point, instead of me turning all the way to here to get to the board, he says, why don't you just turn and face Josh and walk backwards? And get the same spot, right? So that's right. So I would then walk this way, walk negative 2. That's why I kind of I called it a distance originally. I said, it'd probably be better to call it a displacement because you could walk forwards or backwards. And so then, of course, pi over 3 is not the only way to face the exact wrong direction. How else could you face the exact wrong direction? Go backwards, how far? Negative what? 5 pi over 3. There we go. Yeah, so if we look at this in terms of a lovely gray color, we could rotate negative. It's supposed to be gray. What's wrong? There we go. We could rotate negative 5 pi over 3, which would have us facing that way, and we would walk backwards 2, like before. And maybe you can see how not only could you do that, couldn't you then just add an extra revolution to each of those? And we can do that forever and ever and ever. That's why I say there's an infinite number of ways to get to the same point using polar coordinates. Making sense? All this is about today. It's not so much about calculus yet. I might hint at it a little bit, but it's mostly about what is a polar graph and how's it made, what does it all mean. Okay. So let's see here. Polar coordinates, there's an infinite number of ways to get to a point using polar coordinates. There is not an infinite number of ways for us to get to a point using rectangular coordinates, right? And like I said earlier, the grid that we're all used to seeing with rectangular coordinates, this grid, it's like right in here, all these grid lines. Sorry, they're less precise than before, but you get the idea. Just going fast. All these grid lines that we're used to being in there, they're still there. We usually just don't write them because it would be a mess. So if those grid lines are there, and that's still the x-axis and there's still the y-axis are in play, there must be a relationship between polar coordinates and rectangular coordinates, right? It's got to be a relationship. And so those relationships are down below. So if you guys would kind of scroll with your eyes down below, here they are. So if you've got a polar coordinate with r's and thetas, then x, the x-coordinate, is equal to r times cosine theta. The y-coordinate is equal to r times sine theta. If you ever had physics in any form, you've seen this repeatedly, right? Kinematics, yes, forces, all these different things. Tangent of the theta, tangent of the angle is equal to y over x. This is unit circle stuff, 101, right? This is all stuff you've seen before. And then the Pythagorean theorem or distance formula to get the radius if you have the x and y coordinates. So these are all your relationships. And these, especially for us, the first two will absolutely come into play a lot. The other ones maybe not as much, but certainly the first two we will use repeatedly. John?
So the polar, on the very last one, makes it kind of think these are all circles because like x squared plus y squared equals r squared.
Okay.
Just like, is that kind of true, or is that just like to me?
They're not all circles, but for a single point, like if you have a point and so like I would say, the way to maybe to organize this in your thinking is that over here, these two relationships would be useful ways for you to convert from rectangular x's and y's over to polar. Like if I gave you an x-coordinate and a y-coordinate, I said, what would that look like in polar? Well, you'd want to know the angle and you'd want to know the radius. And so you could plug those in appropriately, do the inverse tangent, that kind of thing, and you'd have your r and your theta. So when you said all of these are circles, I would say that all of the polar graphs, like every single point on a polar graph, will have an angle that was used to get point in the right direction and a radius that told us how far to go in that direction. But this will be a nice transition. In order for a graph to be a circle, doesn't the radius, at least from the center of the graph, have to be constant? But what if the radius changed depending on what theta was? It wouldn't be a circle anymore, right? And that's what we're going to look at, mostly. We'll look at circles a little bit, but a lot of other graphs too. Does that make sense?
Yeah, I kind of said it, and I noticed like there's like a million other examples that I was saying wrong. So.
Okay, yeah, fair enough. I think it's a fair question, because certainly r squared equals x squared plus, that's like the equation of a circle center of the origin, right? Yeah, makes sense. All right, so I want to now, yes, no, that's what I want to do. I want to do this.
Whoa.
So, okay, we can play around with this a little bit. I'll see that okay. Oh man, why is it choppy? Come on. Okay, so this kind of goes to what I was just talking about with John. So, a polar graph could be ultra simple, right? A polar graph could, and we'll look at a couple of really simple ones here in a few minutes. But a polar graph, and maybe I'll just maybe do it up here too, but a polar graph could be super duper simple. It could just be like a circle, or even a line or something, right? Or even just a point. Or a polar graph could get really a lot more complicated looking like this. But in every case, not every case, in most cases, the Polar graph is going to be generated by a relationship between r and theta. In other words, as theta changes from whatever angle to whatever angle, maybe 0 to 2 pi would be pretty standard, maybe 0 to pi, whatever it happens to be. As theta progresses on its way through its domain, the radius will change length. And you can kind of see that represented up here, right? So on the right, you can see a graph of 4 sine of 2x cosine of 3x. And can you see how the x-axis over there on the right is angles? 0, pi over 2, pi, 3 pi over 2, and 2 pi. And can you see how on the left side graph, the polar representation of this graph, you can see kind of like the purple radius like rotating around. Makes sense? But I think the important takeaway, or one of the important takeaways here is, can you see how as theta progresses, can you see how the radius on the polar graph gets longer and shorter? Long and short, and it's changing direction occasionally too. So notice right in here as it goes through the third quadrant, see how it jumps to the second, and then the first, and then the third, and then the fourth. It doesn't go 1, 2, 3, 4, does it? It goes, let's see here, 1, 3, 2, or no, 1, 3, 4, 2. 1, 3, 4, 2. And that, of course, is caused by the thing we talked about earlier, like a negative radius, right? Pointing this way, but going that way. That's how that's caused. So we can play with this a lot. You might recognize this a little bit. You probably recognize this a little bit better. Seen that before? That's the proverbial, if you had polar before, that's the proverbial rose. 4-petaled flower. And you can again see the angle from 0 to 2 pi being progressed across, and the polar graph being formed. So let's see here. Let's plot some points quickly. See, let's see here. When theta is 0, do you guys see how r is 0? When theta is 0, so we're pointing straight right. Let me ask you this. I think you can figure this out. For how many times on this domain is the radius 0? What do you think, Liz? Yeah, certainly 4 times, unless you count both endpoints, then you could sort of say 5, right? Can you guys see, here, I'll freeze this real quick. Can you guys see how when, you see how when theta is 0, r is 0? Like when we face straight right, do you see how there's no points out there? When you face straight right, the radius is 0. So if the radius is 0, where is the point? At the pole, at the origin, at the pole. That's right. So then, for what theta is the radius biggest? What would you say? Pi over 4. You can see that over here. But then pi over 4 would show up right about there, wouldn't it? See how the radius is biggest? The radius is 4 when theta is pi over 4. Okay. But there's other places, right? How many other places is the radius biggest? 3 other places, unless you keep going around and around and around, then it's an infinite number. But yeah, you can see that basically at all these pi over 4 angles, you've got the biggest possible radius. But then really, honestly, you can see the pink radius getting ready to sweep around, right? You can see that radius is going to be shorter or longer depending on whatever theta is. So that's why I say all these cool polar graphs are going to just simply be relationships between r and theta. Let me throw a little calculus into the mix. This will just be conceptual stuff. So, like say a polar graph just like this one with the lovely rose. Do you guys see any locations on that graph where the tangent line to the graph would be horizontal? I don't think pi over 4. I would say at pi over 4, the tangent line would probably be that-ish. Yeah? Do you see, let me ask you this. How many places do you see where the tangent line would be horizontal? Okay, so let's see here. You say 4 of them. Are you guys looking at like this one right here?
Yeah, no way. That's like
And there's more, right? So there's this one. Does anybody see any other places where the graph would have horizontal tangents, Josiah? Yeah, right in here. This is another horizontal tangent. Say again? Well, so what's interesting is there would be more than one angle where you'd have horizontal tangency, right?
Mm-hmm.
But there would just be one horizontal tangent line. That makes sense? So there'd certainly be more than one time where you'd say, oh, look, the slope of the graph is 0. But it would all, in the middle there, would all be the same line. And as a matter of fact, because of symmetry, couldn't you say that this line up here on the top and this line down here on the bottom, wouldn't those be the same line as well because of symmetry? But it would be different angles. It would be 4 different angles where you've got horizontal tangent line, but because of the symmetry, they'd line right up and it'd be the same line in. So whatever. It's not like you have to find more, two different equations for those horizontal lines. It'd be the same one. You guys see any vertical tangent lines? Kind of the same deal, isn't it? So the vertical tangent lines would be here and here and here, and also out here, and then one right down the middle. There'll be vertical tangent lines. Is all making sense? Maybe one more brief preview. One of the things we'll do is we'll look at some graph like this, and the question will be, what's that area? So let's get a little foreshadowing here. You see how rectangles are, like rectangles based on the x-axis or the y-axis are going to be a little bit messed up here? Right, so if I tried to use rectangles and said, all right, let's put in a little Riemann sum here with rectangles. Looks okay so far, but then once I get out to here, you can see I got that white space underneath. The rectangles are clearly collecting area that they should not be collecting. And so, for reasons like that, the rectangle idea is not going to really fly with these. Anybody have any ideas on, instead of rectangles, what shape we would base our area accumulation on? Say again? Circles. Not circles. Although it would fit the nice curvy look to it, right? I will say you're not too far from the truth. Not ellipses either, simply because those do look elliptical, sort of, but you got like a pretty sharp point right there in the middle. So there's going to be some overlap. We need to accumulate, sort of like the rectangles, accumulate like these smaller shapes. Triangles, though, we need to have. The problem is with triangles. Triangles is an interesting idea. I would say if you took your idea of triangles and sort of combined it with Josh's idea of circles, you'd have it. Soccer ball? Anybody? I'm being. What's that? Man, like you're so close to the truth. You really are. Like what? So let's get away from
a cylinder.
Get away from 3-dimensional figures. We need to use a 2-dimensional figure. What is sort of like the weird marriage of a circle and a triangle?
A flattened cone like this.
Like a 3D cone projected into
I don't know if you saw that. I don't know if you saw that. No, listen, I don't know if you saw her hand motion, but her hand motion is right. If we just knew what to call that thing.
Oh, a kite? Is it like a kite, but not pointy?
No, it's not a kite. It actually has a name. Like a weird combination of a circle and a triangle.
It's a children's
Oh, we're-
tear that last time, so it's still
Oh, you're talking like if you drew it, yeah. No, that is it. I'm just wondering what the name of that thing
Ice cream.
It's a tear.
A spade.
is. Say again?
It's a
pizza.
It's got a motion really fast.
Oh, this one's
No, it's also an ice cream cone, so.
Okay.
Is it?
So,
Can you call it a spade?
a spade.
Spade. Have you ever seen a
You play
spade?
cards, man?
Okay, so here's the shape you all are describing. So it'd be like this, the shape that has like kind of a rounded end.
Oh, there it is. Oh, wow.
That actually fits pretty good.
See that?
And then this out here would maybe be a little bit of an overestimate, and it would do something like this and whatever. You can see if you took those shapes and you made the number of them increase towards infinity, they'd get really skinny, but it would still have that nice rounded end that would conform nicely to a curve like this. Anybody know the name of that shape? So it's a subset of a circle, and that's why I said Josh was pretty close to the truth, but it sort of looks like a triangle, which I said you were sort of close to the truth too. So let me just squeeze this in. If I got a circle over here, so there's the circle, there's the center. If I take a circle and just cut off one piece of the pizza, one piece of the pie or whatever, this is called, bless you, I know you've heard this,
Circle.
sector. Sector of a circle. So instead of using a rectangle later on to find the area, we will use a sector. There's two kind of triangle-y looking parts to it, but then it's got the circular end. So whatever. Okay, so that's just a little preview. And guys, there are obviously a huge number of ways this could go. There it goes. 4 sine of 2x is a nice rows. And I do something like that. Obviously, that's a little bit more than I wanted to do. Okay, a little bit smaller. A little bit smaller, yeah, right. So it's just like, get rid of that entirely. Now it looks like this. I mean, there are all kinds of different shapes and forms these graphs could take. We could get rid of this. Oops. That looks like that. Now it looks like this. Now it looks like this. Are you watching?
What is that one?
That's
Now it looks like this.
a loop Lima song right there.
Yep, looped Lima San, et cetera, et cetera, et
Is
cetera.
it a Lima song? It's supposed to be
Lima Con.
Lima.
Lima.
Lima song.
I'm not going to try to say it like a French guy. I'm not going to call it a Limacon, but, you know. Anyways, so guys, here is the big takeaway before I kind of turn you loose for a few minutes with your calculators. The big takeaway is a polar graph, kind of like these that we've just kind of been playing around with, are simply a relationship between the radius, or the displacement from the origin, and theta. As theta changes, radius changes, and you get these various graphs. There's all kinds of different rules we can learn. You're going to find that I'm a lot less concerned about, like, what if A is bigger than B, and what if B is bigger than A, and what if A is equal to B, and all these different things. We're going to draw some general conclusions. We're not going to get into a ton of the nitty-gritty details. So here's what I would like you guys to try now. Not what I wanted to do. Where did it go? That's what I wanted to do. If you guys would, use your calculators. And I would like for you to please try. We've got 13, 14 minutes left. I would like for you guys to work on graphing on the calculator and then just sort of like transferring the graph you see on your calculator over to your notes there. Like these first 6 graphs. You might have a little trouble with the first one. Or sorry, not the first one, the second one. Theta equals pi over 3. Possibly. You might have a little, I don't know if you'll have trouble with that one or not. But anyway, I want you to try to graph these 6 on your calculator. See what these all look like. Play around with the window, the theta. I'll probably jump in after about 10 minutes or so. We'll talk a little bit about how the window and all that stuff affects the graph. So give it a few minutes, try to graph those. So like these top three graphs real quick, like the first one upper left, here's the way that I think about it. Obviously, the first one is a circle, and my thought process on that is simply r equals 2. All that means is theta is not mentioned. So theta could be anything that it wants to be, as long as the radius is 2. Does that make sense? I'm talking about that first one. If r equals 2, it's not telling us any relationship between r and theta. It's saying, theta, you can be whatever you want to be, as long as the radius is 2. That is really, honestly, the description of a circle. Be prepared to be wowed and amazed.
I'm so ready.
Oh, I missed.
This medium.
Oh, I didn't miss that time. Okay, there you go. So there's your circle. Then theta equals pi over 3. This is very similar to the first one in the sense of the radius can be anything it wants. It can be positive whatever. The radius could be 0. The radius could be negative whatever, as long as you're facing pi over 3 for a direction. And so this will just be a line that looks about like that, pointing in the pi over 3 direction. The radius can be whatever it wants. It really could just keep going forever and ever. And then when you get to this one on the right, this one you actually could plug into your calculator. R equals secant of theta. This would be over here, vertical line at 1, I believe, right? Because secant of 0 should be 1. Okay, so that would just be a vertical line right there. And again, this is the first time where there's a relationship, at least on these graphs by hand, where there's a relationship between r and theta. So the radius will get longer or shorter depending on what theta is. So if you wanted to look at the little radial lines that are determining this, here's what they'd look like. If theta is 0, you'd be pointed straight right and the radius would be 1. If theta was like pi over 6, there's your angle right there, and the radius would be slightly bigger than 1. And then if your angle was pi over 4, there's your pi over 4, and the radius would be a little bit bigger yet. You see this? If theta was pi over 3, radius would be a little bit longer yet. If theta was whatever that angle is, the radius would be a little bit longer yet. Do you see how we're reaching kind of an interesting point as my theta goes from 0 and increases and increases and increases? Doesn't there have to be a limiting factor here? Where can't I go with secant of theta? Where can't I go as far as an input for secant of theta?
Negatives.
Pi over 2, right? So if I try to point straight up, there's no points up there, right? And if you think about it, the graph of secant at pi over 2 has a vertical tangent, doesn't it? And so as theta gets closer and closer to pi over 2, those radial lines will get longer and longer and longer, heading towards an infinite length. That makes sense. Okay. And then lastly, these two, let me finish with this. I want to do this on the calculator real quick. So just take a second. Okay, so then here, and how about here? So I'm assuming that on these last two, you did something like this. I'm going to do something a little bit different here. Check this out. I'm going to say, what is r equals 5 going to be? It's a circle. And I'm going to graph the first one. R equals 2 sine of 3 theta. And I'll just go zoom 6. Let me go back. I'm going to graph these simultaneously. So check this out.
Wow. It looks like a sand dollar.
Oh, it does.
So guys, I want you to listen up. I want you to notice something here. Hey guys, I want you to notice something here real carefully. This will be where we leave this for today. I want you to watch the graph of the circle and the graph of the little rows. Carefully watch the timing. Ready? Did you notice how the rose was done before the circle was done? I want you to notice it again. Okay, so watch the relationship in the speed. When did the rose finish relative to the circle? When the circle was halfway done. So check this out. If I went back here and I took my theta min in my window, and made my theta min 0, can you see how theta max is 2 pi? What if I just made theta max pi? Watch what happens here. We get half the circle, but we get the whole rose, don't we? So some of these graphs, their domain is going to be 0 to 2 pi. Others are going to be 0 to pi. It's going to be important that we recognize what goes with what. Okay? We'll explore that next time. So thank you guys. Great job. It's good to see you all again. Have a good rest of your Wednesday. See you in chapel in a few minutes.